Hello, in this video, you will understand application of slope deflection method for analysis of portal frame. In this video, first we will discuss step-by-step procedure for analysis of unsymmetrical portal frame using slope deflection method and one numerical example on analysis of portal frame with overhang. We know that portal frame is said to be unsymmetrical if it satisfies any of the following conditions, that is unequal column length, inclined column legs, unequal cross section, that is different moment of inertia of the column, different types of column support, and unsymmetrical loading on beam or on column. If the frame is unsymmetrical, then if it is loaded, then in addition to rotation of joints, there is translation of joint also. Translation of joint means there is horizontal movement at the top of the column, which is called as sway. So sway is one of the unknown quantity in case of unsymmetrical portal frame. So first step is always to identify whether the given frame is symmetrical or unsymmetrical. That means whether there will be sway or whether the frame is sway frame or non-sway frame. Let us consider this frame. You can observe here moment of inertia of column and beam is same. Height of column is also same. Support condition is also same. But loading on the beam is unsymmetrical. That means if you draw an axis of symmetry from this portal frame, then it is not a mirror image on other side. So such frame is called as unsymmetrical portal frame. So in this frame, in addition to thetas, delta is also unknown. But suppose in same frame, the load is extended on other side also on the left of B and make this frame symmetrical, then there will not be any delta in this frame. It is a symmetrical frame condition, so a sway will be not there. Now let us consider this frame. If you draw axis of symmetry, it is not mirror image on other side. If anybody asks you whether it is a sway frame or non-sway frame, then first of all you have to look for whether there is such support which restrict the horizontal movement of frame or not. So you can observe here there is one support because of which there is no translation of the joint. So there will not be any horizontal movement in this frame and therefore this is a case of non-sway problem. So in this case also delta is 0. So first important step is identify whether the given frame is symmetrical or unsymmetrical. If the frame is unsymmetrical, then in equation of slope deflection, you have to take delta as unknown and delta is to be taken only in column equation and not in beam equation. So let us solve one unsymmetrical portal frame using slope deflection method. Now we will discuss the step-by-step procedure to analyze this unsymmetrical portal frame using slope deflection method. So whatever may be the frame is, first step is always to calculate fixed end moment and joint moments. So in this frame, member AB and member CD is not subjected to any load and therefore fixed end moment for member AB and CD is 0. There is load UDL on beam BC, because of which we have a standard formula for UDL minus WL square by 12 and plus WL square by 12. So because of this, the beam BC will have fixed end moment of minus 90 kilonewton meter and plus 90 kilonewton meter. Now there is overhanging part. Because of this overhanging part, there is joint moment. So we calculate joint moment like this. MFCE is equal to force into perpendicular distance is the moment. And when joint moment is clockwise, we have to take negative. So this moment is clockwise about C and therefore we will take minus 30. What is 30? 30 is UDL into 1.5. 30 into 1.5 is total load due to this UDL, and it will act at 1.5 by 2, half of 1.5, plus 50 into 1.5. So this is the moment, joint moment, which is minus 108.75 kilonewton meter. Now, if you observe the sign convention for fixed end moment, anti-clockwise is negative and clockwise is positive. But for joint moment, clockwise is negative and anti-clockwise is positive. Please remember this. Next step is to identify unknown displacements in the structure. When the frame is symmetrical, then only thetas are unknown. But if the frame is unsymmetrical, there is delta, which is taken for column as unknown. So in this case, at support A and D, it is fixed support, and therefore theta as A and D is 0. There will be theta unknown at B and C. Initially, you have to neglect this portion whenever there is overhanging portion in beam or in portal frame. First of all, you have to neglect that portion and calculate how many unknowns are there. So theta A and theta D are 0, and there will be theta B and theta C, which are unknown. And there is one more unknown, which is delta, that is sway for column. So if the frame is unsymmetrical, there will be sway, and delta is unknown for column equations. Now next step is to write the slope deflection equations. Whenever there is overhanging part, while writing slope deflection equation, neglect that part. This will appear while writing the equilibrium equations. Now you know that there are three members in this portal frame, A, B, B, C and C, D. So number of equations to be formed is equal to 2 times number of member. So in this frame, we have to write 6 equations of slope deflection. So in this case, since it is unsymmetrical portal frame, you have to consider the sway. Now here I am considering sway to right. You can consider sway to left. So let us see what is difference if you consider sway to right or sway to left. So if you consider sway to right, in the equation of this column equation, you have to take minus delta, because here the moment developed due to sway to right is anti-clockwise in nature, and since it is anti-clockwise in nature, we have to take negative delta. And if you consider sway to left, then you have to take positive delta. So let us consider sway to right. So for each of this member, you have to write such equations: 2ei by L twice theta A. Theta A means this is the first letter. We are calculating at A. MAB means moment at A whose far end is B. So here you have to take twice theta, and at other end 1 theta. So this delta term will appear only in the equation of columns, that is in AB and CD. There will not be any delta term in equations of beam BC. So you can write this fixed end moment at the end, or you can write it on this side also. So let us write these equations for all the members. So first we will write equation for member AB. So if you write MAB is equal to 0 is fixed end moment plus 2 EI by L, L is 4.5, theta A is 0, therefore this term is 0, plus theta B minus 3 delta upon L. Similarly, you can write MBA. So if you simplify, you will get this equation. Similarly, write for MBA, 0 is fixed end moment and theta A is 0. So you will get this equation for MBA. MBA means moment at B whose far end is A. Next, we will write slope deflection equations for beam BC. Now in beam BC, there will not be this delta term. So MBC is this is fixed end moment minus 90 plus 2ei by L twice theta b plus theta c. So please note here there is no delta term in this equation. So if you simplify this, you will get equation like this for BC. Similarly, you can write for CD. 90 is fixed end moment, 2 ei by L twice theta c plus theta b. You will get equation something like this. So these are the equations for beam BC. Now we will write two equations for column CD. So MCD, 0 is fixed end moment, 2 ei by L, theta d is 0. So therefore this is 0 twice theta c, and note here 3 delta upon L and minus sign because we are considering here sway to right. So if you simplify this, you will get MCD like this and MDC as 4 by 9 ei theta c minus 8 by 27 ei delta. So this is how to form the slope deflection equations. So there are 3 members, so we get 6 equations. Next is to write the equilibrium conditions. Now in this case there are 3 unknowns, theta b, theta c and delta. And therefore to solve these 3 unknowns we will need 3 equations. So let us write these 3 equations. So we write equilibrium equations where thetas are unknown. For example, here at B and C. So at B, what is the equation? MBA plus MBC is equal to 0. At C, MCB plus MCD plus MCE is equal to 0. Here you have to consider this overhanging part. So first equation is MBC plus MBA is equal to 0. And second equation is MCB plus MCD plus MCE is equal to 0. First we will write these two equations and then we will see how to write the third equation. Third equation is called as shear equation. So what is MBC? MBC is that equation which we have derived in slope deflection form. So here if you add MBC and MBA, you will get this equation. So this is our first equilibrium equation. Similarly, you have to form the equation at C. So at C, if you write this MCB, MCD and MCE, you will get equation like this. This minus 108.75 is MCE. That is the joint moment which we have calculated initially at C. So if you simplify this, you will get 9 ei theta b plus 42 ei theta c minus 8 ei delta is equal to 506.25. So this is our second equation of equilibrium. Now we will see what is the how to form the third equation of equilibrium. Third equation we form by applying summation of horizontal forces equal to 0. That equation is called as shear equation. So here horizontal forces are not there, but there are reactions at the support, that is HA and HD. So if there is horizontal force also, then you have to consider that force while writing the equation. Now here we will write HA plus HD is equal to 0. But suppose there is force acting here, suppose 10 kilonewton, then that equation will become HA plus HD plus 10 is equal to 0. Okay. So this is the shear equation. Now for this, we have to first derive the equation of HA, equation of HD in terms of final moment. So for that, we need to draw free body diagram of column. So if you draw the free body diagram of column, these are the forces acting on this member. Let us consider this is B point and this is A point. Then what are the forces acting here? When we separate any part of the frame from rest of the frame, then we have to introduce there 3 forces. We have drawn all the forces in positive directions, one horizontal force, one vertical force and a movement. Similarly at A, since it is fixed support, you have to show here horizontal reaction, vertical reaction and movement. But if this support is hinge support, then there will not be any movement. Only horizontal reaction and vertical reaction will be there. Now let us consider this is column AB. Suppose there is horizontal force acting on this column, then that also you have to show here while taking the moment of all the forces. Now I have shown few forces by dotted line, because if you take moment of these forces about point B, its moment is 0. And what are the forces which contribute to moment? It is this HA plus this moment MBA and this moment MAB. So what is the equation of HA? Take moment about B equal to 0. What you will get? HA into 4.5 minus MAB minus MBA is equal to 0. Or you can say HA is equal to MAB plus MBA divided by 4.5. Similarly, we can write the equation for CD column. It will be MCD plus MDC divided by 4.5. So if you write this equation, you will get like this: MAB plus MBA divided by 4.5. This is equation of HA. Now remember that if there is horizontal force, it will also be there. The moment of that force will also be there in this equation. Okay. And while writing this equation, this force will appear in this equation also. So this is that shear equation. Now what is MAB, MBA, MDC and MCD? These are nothing but the slope deflection equations which we have already derived. So you will get a long equation if you expand this, and then if you simplify this equation, you will get 9 EI theta B plus 9 EI theta C minus EI delta is equal to 0. This is our third equation of equilibrium. So we have three unknowns and three equations. So we can solve these three equations to get these three unknowns. So first equilibrium equation we get from summation of moment at B equal to 0. Second equilibrium equation we get from summation of moment at C equal to 0. And third equation we have derived summation of horizontal forces equal to 0. So three unknowns theta B, theta C, delta, and three equations. Solve this simultaneous equation to get value of theta B, theta C and delta. So if you solve this, you will get EI theta B as 73.6364, EI theta C as 15.3409 and EI delta as 100.0994. Now we have to back substitute these unknowns, these quantities of theta B, theta C and delta in slope deflection equation to get final end moments for all the members. So if you substitute value of theta B, theta C and delta in equation of MAB, you will get MAB is equal to 3.07 kilonewton meter. MBA is equal to 35.80 kilonewton meter. For member BC, the final moments are minus 35.80 kilonewton meter and plus 124.77 kilonewton meter. Now after calculating the moment at the joint, you please check whether you are getting same magnitude and opposite sign or not. So here MBA is plus 35.80 and MBC is minus 35.80. Because we have applied equilibrium condition, MBA plus MBC is equal to 0. So you must get, if you add these two moments, you must get 0. Similarly, at joint C, if you add MCB plus MCD plus MCE, you must get 0. So these are the final moments in this frame. Once you calculate all the moments, then next step is to draw the bending moment diagram. So to draw the bending moment diagram, first of all, we draw joint moments and then we overlap bending moment due to UDL. So you know that the maximum bending moment is WL square by 8 at the center of UDL. So it is 135 kilonewton meter. Here in this portion, which is a cantilever part, so in this portion, since there is UDL, this curve is not linear. But if there is no UDL, only point load is there, then this will be a linear, means a straight line connecting these 2 points. But here it is UDL, so it is non-linear like this. Otherwise, all other end moments you have to join by a straight line and overlap the bending moment due to load. So this is how we get final moments. All these values are in kilonewton meter. I hope you must have understood the concept of overhanging part and how to deal with that overhanging portion when we solve any portal frame or beam using slope deflection method. I hope this video is useful to you. Thank you for watching this video.